Okay, well, here we go. Yes, welcome everyone. This is lecture number 8, and we're going to talk about stochastic integrals again. In particular, this is going to be about the Riemann and the basic Riemann-Stieltjes integral, but also the Ito integral as well. So we're going to look at for properties. We'll have basically been analyzing quadratic variations and absolute variations before for Wiener processes, but not basically looking at basic existence. So I'm going to develop sufficient and necessary conditions for their existence. We're going to look at the moments, especially the expectation and the variance. I mean, of course, the variance is not the second moment, but basically it requires to have basically to address the second moment. So that's why I would say moment, but also the autocorrelation. We're going to look at the distributions, and we're going to look at basically and specifically the stochastic version of the Riemann integrals, which I'm going to extend here. Then we're going to look at the Riemann-Stieltjes integrals, and then we're going to look at the Ito integral. Now, whenever basically these integrals come up, there is always going to be a Wiener process around. So we're going to actually look at these integrals in terms of Wiener processes, and mostly Wiener processes only. So there's always going to be a Wiener process there. And so therefore, I'm going to basically also look at the general version, but that is also including, at least for the integrator, the Wiener process itself. Okay, let me check. Everything is fine. It looks, at least so it appears to be the case. All right. Okay, then we can continue. All right, so we're going to look at basically functions of Wiener processes again. There was one which I missed from last lecture, so therefore I was basically, you know, maybe remember the Brownian bridge and so forth. So, but I found that basically that fitted better here. So there is going to be a Wiener process, and then this is actually function number 7. So in the last lecture, we're looking at 6 functions like the Brownian bridge and the reflective Wiener process and the maximum Wiener process and stuff like that. But now we're going to look at the integrated Wiener process. Now the Wiener process is already an integrated stochastic process, but anyway, okay, so that's a little bit confusing by the name. But if it says integrated, there's going to be an integral there. So the stochastic process I'm going to define here, which is the stochastic process x at time point t, is going to be the integral of the Wiener process from 0 to time point t. So that's basically it. You can basically look at that as the random area that the process generates together with the x-axis, basically. Okay, but keep in mind it can be also negative, because again, so its integrals don't really correspond to areas unless the function is actually not negative. But since the Wiener process can be negative, it can happen that basically this function is, I mean, you have negative, so-called negative areas if you like. So that can happen, okay? Just have a look. Okay, for example, I was looking at a path of a Wiener process here. So again, if it goes down, that basically the area, okay, this area, as we were looking at later on, would be a negative one, although there is no such thing as a negative area, but in terms of an integral, that doesn't really matter. So again, so let's say this is a path of a Wiener process, and basically what would be the area that it generates, and the area that it generates is called the integrated Wiener process here. Okay, so basically given by x. Okay, so again, it's slightly negative. It's not that big of a deal, but again, it can be also basically below the x-axis. I don't think basically this is an over exaggeration, but you can look at that from that point of view to be actually a random area that the process, the Wiener process, would generate, because that is basically to which it corresponds to. All right. Okay, now there is going to be some properties on that which fit better to this lecture, because we're going to look at stochastic integrals again. So that's basically what I'm going to remind you of. Okay. In particular, basically, when the integral is from 0 to 1, okay, which would be the process at time point 1. The process at time point 1 can be also addressed to be a random variable, and it has a distribution, namely normal distribution, with mean 0 and variance 1/3. Now, why 1/3? This is basically the topic of today, among others. Okay, so we're going to talk about those things, and you will be able to also derive such distributions yourself, and that is going to be part of the exam. So you will, again, I'm not going to make it too complicated, but just for you to know, this can be relevant. I'm going to create an exercise based on this lecture, which I haven't done, and then I would like you to check it out. I will remind you basically later on when we're done. Okay, so when we're done, I'm going to create an exercise, and I would like you to ask it to solve it. Anyway, okay, so first off, I'm going to define stochastic Riemann integrals again. Since we had that definition already, I'm just basically going to repeat that stuff. So first, by which it starts, I mean, it always starts with the partition. So you always have a partition on an integral, and the interval in this case is going to be from a to b. Now, in a more specific case, which is going to be the interval from 0 to t, without loss of generality, by the way, but again, that was a general case, so I was defining it as such. And keep in mind that basically where the partition starts is actually the lower end point of the interval, so a is going to be S0 by definition, which is strictly less than S1. Again, otherwise it would not be a partition, which is on the other hand strictly less than S2 and so on. And then you'll have basically the last point, which is Sn, and that corresponds to the upper end point of the interval. So basically the partition is always like this. Okay, and then what you also have is basically a stochastic process. Now, if actually the following sum converges in mean square, okay, so that is basically what the convergence is. Convergence in mean square, right? You remember that. And I'm not going to recall what it was, but I was repeating that definition basically 2 weeks ago. So I think, if I recall it correctly, lecture 5 and 6, okay, in each of the two. Okay, so we're going to talk about that again. Now, x, basically the stochastic process, can be at any point between Si and Si minus 1. Si is the upper end point, and Si minus 1 would be the lower end point of that partition, and Si asterisk is basically some point between. Okay, so it can be anything basically between. And then you have, let's say, the increments of time. I'm not supposed to say that, but basically this is what it would be. So in terms of that interpretation, and because the x-axis denotes the time axis, basically, okay, I think you've noticed that before. So it basically the increments of time. And then again, so here I was explaining that S asterisk is somewhere between the upper and the lower endpoint. It can be also the upper and the lower endpoint or something between. It doesn't really matter. Not in terms of the Ito integral. For Ito integral, it does matter, but basically for the static Riemann version, it doesn't. At least it's not supposed to, because if that is converging in mean square to basically the following expression, or it converges basically, which is supposedly be finite in terms of the random variable, and we express the limit in terms of an integral. So the integral is just basically representing the limit of this, actually of this sum, or regarding the partition or the mesh size as basically as increases. Okay, so as I increase the number of subintervals from or inside basically from A to B, which is generating the limit, then the limit is basically expressed, and this is just a symbolic notation, by the way, as in terms of an integral from A to B of the stochastic process, okay, with respect to basically time. Okay, so that is basically the integrator is time here. Okay, now keep in mind this is just a symbolic notation, okay, because it needs to be finite, of course, and we're going to look at existence today and so on, which we haven't done before. So when is basically this integral existent? Anyways, okay, so the mean square limit is actually the integral, and that is supposed to be the stochastic Riemann version of the integral, right? We were talking about that already, I think lecture 6 or 5. I'm not sure if I recall it correctly, but anyway, I was introduced to that already. Now I'm going to look at basically the extended version, which I haven't. Okay, so because that is not the general version, you can also call it the general version if you want to, because I was only talking about that. Now, for the extended version, there is also a function, okay, which is multiplied by the stochastic process, and that function is a deterministic one. So it's not a stochastic one, it's a deterministic one. It doesn't change that much, but it plays a certain role when it comes to basically generalizations. Keep in mind, things like this, for example, can be interpreted if f, let's say, is a density function, can be also interpreted to be some sort of expectation or whatnot. But anyway, okay, so that is basically what I'm going to look at. And if you have basically a deterministic function that is defined on the, actually on the interval, it's not consistent here on this slide, so I apologize, guys. Here it says on 0 to t, where actually this is not the case, but I'm going to change that. So the upper and the lower endpoint when it comes to stochastic processes or stochastic integrals is always going to be from 0 to t. I apologize since it's not consistent, but again, it doesn't really matter. So, but that's what it's going to be. Now, again, we're going to look at existence, we're going to look at moments, and we're going to look at distributions of this thing. Okay, so when does it exist? Let me just basically make that statement again. Before I do so, I need to address another theorem which is very important, and that is going to be Fubini's theorem. Okay, Fubini's theorem addresses basically expectations of those integrals, and integrals basically were those limits of those sums, right? So if I say the word integral, that is always going to be a limit of specific sum. It allows you to bypass the expectation operator by the integrator. I mean, you can call it the integral operator, but it's not an operator in that sense, but you're going to see what this means. So let's say you have a stochastic process, and that is going to be a continuous time and a continuous state stochastic process without loss of generality. It also works for discrete time / discrete state processes under certain circumstances, but it's easier to prove for continuous time and continuous state stochastic processes. And limits are going to be continuous time all the time anyway, okay, because at least they have basically you have some sort of continuity at least almost everywhere. Okay, so because otherwise it would not be an integrable function most of the time. But you might remember when a function is Riemann integrable if and only if it is continuous almost everywhere, right? You remember that term. That was also a subject. So again, it's easier to prove in this case, but we're going to apply this for limits anyway, so why would basically, this is not a general state. Now, if the this expression here, okay, where you would calculate the integral of the expectation, which is a deterministic function. Keep in mind, guys. Okay, so that's not a stochastic integral. This is a deterministic Riemann integral, guys. Okay, and that is supposed to be finite. And basically addressing the expectation of the absolute value. We had basically looked at that for the normal distribution. You might remember that. I'm going to recall that as well. Okay, but that is supposed to be finite. So again, this is not stochastic, guys. This is a deterministic integral, and a simple Riemann integral. I mean, it's not that simple, but it is. Okay, and this has to be finite. So which means that actually this function needs to be actually integrable, Riemann integrable, and this is the case if and only if it is continuous almost everywhere, right? So for the points where the number of points which is not continuous is countable. Anyways, okay, so if this is finite, which again I was naming sufficient and necessary conditions for that, then the expectation of the integral. So again, it might be not surprising, but it is. The expectation of this integral, which is the limit of a sum, and that is the limit, the mean square limit of a stochastic sum, right, or a stochastic process anyway, is going to be the integral of the expectation. It might not surprise you because the expectation operator is a linear operator, right, and integrals are limits of sum, so why would basically not be intuitive? And I mean, intuitively it is clear, but it's not that straightforward because the issue is, as you see, this is a stochastic integral and that is not. Okay, so that incorporates a stochastic integral based on the mean square convergence, and whereas basically the other one is not. Okay, it's a deterministic one, it's a Riemann integral, but the two are equal anyway. Okay, so that's the issue. Now, since this theorem is so important to address the existence of stochastic integrals, I will need to prove it Okay, so that is going to be basically the next part. And we're going to see this. Okay, so the question is how to, and I'm going to show you why. So let's say you got a partition already, okay, because again, we need to have a partition. This is a Riemann integral that we're going to talk about. So if it says basically, if this is finite, then basically you can do that. So you can bypass the expectation operator by the integral operator. It's not going to be a big deal for stochastic processes, but given that this thing is finite. And I'm going to show you, all right? Now let's say you got a partition from 0 to t, or on this interval from 0 to t. And again, in this case, I will basically stick to that. So when it comes to stochastic integrals, I'm always going to be basically look at partitions on 0 and t in general. So 0 is going to be basically the starting point or of the partition as 0 by definition, which is strictly less than S1 and so on. All right, so you see this before. Now, if this is finite, and I'm going to show you, so if this is finite, then you can bypass the expectation operator by the integral operator. This is what basically Fubini's theorem is telling you, okay? Now, since it is finite, it must be the case, okay? So basically between 0 and t, is finite, okay? I stress the word finite, right? The function, which is basically, again, depending on time, all right, so regarding the stochastic process, but again, this is a deterministic function, guys, so keep that in mind when you're looking at it. This is a deterministic one, okay? And it needs to be Riemann integrable. And basically, it is. I mean, otherwise, it would not be basically that you'll have an integral coming out, which is finite, okay? So if this is not true, then the function would not be Riemann integrable, but since it is true, it is, okay? Now, I was basically, again, telling you when it would be the case. A function is Riemann integrable if and only if it is continuous almost everywhere. So if it's basically Riemann integrable, it is continuous almost everywhere. And if it's continuous almost everywhere, then it's going to be Riemann integrable. Now, with respect to time, of course, so S basically denotes time here, okay? Because S basically varies from 0 to t, right? Okay, so you're on basically on the time axis. Now, in this case, since it is Riemann integrable, this is going to be actually the function for which the limit is constructed from, right? So this is the Riemann sum, by the way. The Riemann sum is going to be convergent, right? Okay, it converges as basically the partition or the number of subintervals increase on the partition. It must be the case, so that is going to be basically the limit, okay? And this is basically, it implies also that not just that, but it's going to be that not just basically this function is Riemann integrable, but if this is Riemann integrable, then basically the expectation of the random variable is also going to be integrable without the absolute values, all right? So without it, basically. All right, so if this exists, it is also going to be integrable, by the way. It's not a big deal, all right? Now, and that is going to be the limit of it, right? It's not actually difficult to see. Now, on the other hand, if you look at this one, you have the expectation in there. And the expectation of a linear transformation is the linear transformation of the expectation. And the expectation of a sum is going to be the sum of the expectation. As a consequence, regarding this Riemann sum, I can take out basically the expectation operator from the summands to be basically the expectation of the whole thing. So that is going to be the total expectation of the whole sum, because the expectation of a sum is the sum of the expectations. And the expectation of a linear transformation is the linear transformation of the expectations. Okay, so this is basically what you have here. These things are equal. Okay, now if two sequences are equal and both are convergent, that they cannot have two different limits. So when you look at that, again, this is also a deterministic one because we have an expectation here. Although inside the expectation operator, you have a stochastic integral, or basically convergent stochastic integral, let's say. This is going to be the expectation of that integral, okay, straightforwardly. Okay, so again, it's not that clear, but basically from the intuition is clear. Okay, now if two sequences are equal and both are convergent, then the limits must be equal. So this expression must be equal to that. Otherwise, it would not work. And that is basically what the Fubini's theorem is said. Relatively simple, actually. Again, for looking at basically from the intuition. Okay, so I'm going to basically address this, and I'm going to apply it for Wiener processes. So let's see basically what it would be, because I would need to find expectations and variances and so forth, basically where the Wiener process is involved of stochastic integrals. Again, keep in mind, guys, stochastic integrals are random variables in general. So I would need to basically to address their expectations and variances and so forth. All right? Now, and Fubini's theorem allows me to do it, but there is a precondition to this. Okay? So the precondition is, of course, that when it comes to basically the Wiener process, and I want to address basically expectation of stochastic integrals where the Wiener process is involved, this function here, again, this function must be Riemann integrable. Otherwise, it would not be the case. And we have done that, so we are basically not doing it again. But again, if this is finite, it will be, you can bypass basically the expectation of the stochastic integral where the Wiener process is involved by, you can bypass basically the expectation operator by the integral operator. Okay, so that's not going to be a big deal. Now, but we need to check that first. So whether basically this is true or not, we need to check it. Okay, so basically, so let's see whether this is true. Okay, so let's see what the Riemann integral of this function, where the expectation of the absolute value of the Wiener process would be. We done that. So that was basically what a little work which basically I prepared. I'm not sure which lecture that was, might be lecture 4 or 5 or so, where I was basically addressing that. Okay, so I was calculating the expectation of the absolute value of a Brownian motion. I think it was a Brownian motion, but I'm not sure. Anyways, okay, so either Wiener process or Brownian. So we've done that before, because the function which we found was actually 2 times s by pi. If you're not sure why this is, again, I would like to check that out. This was based on a transformation theorem. I remember that. So again, if you're not sure why this equation holds, then you might not remember what we done regarding the expectation of the absolute value of a normal random variable. Okay, so I was basically doing that one. And you can check that out. That was basically transformation theorem at the beginning. I was doing that, so, and that is the reason why. Okay, so now you basically, it pays off because I'm applying it right now. Okay, so if not sure, basically where to find it. It was at the beginning, maybe lecture 3 or so. Again, I'm not sure again, but it doesn't really matter. Now, okay, this is relatively easy to integrate, guys. Okay, what I did is basically taking out the constant. Okay, the constant is basically the square root of 2 by pi. And then you have basically this, the square root of s, which is equal to s to the power of 1/2. S to the power of 1/2, the antiderivative of s to the power of 1/2 is going to be 2/3 times t. I mean, in this case, there is just t because the lower endpoint of the integral is 0. So that is going to be basically eliminated anyway, because, again, 0 to the power of 3/2 is going to be 0. Okay, so that's basically what it remains. And then if basically the integral is bounded, which it is, then this integral is going to be finite. All right, so that is basically the issue. This function is actually Riemann integrable. So since this function is Riemann integrable, you can apply Fubini's theorem. So you can apply it right now. Because, again, so what does that mean? That means that you can bypass with your expectation operator the integral. That's it. Okay? So that is basically it. And I'm going to show you where I'm applying it without basically explicitly denoting it. So this allows me, so the finiteness, whatever that is, I mean, again, it is always going to be finite in this case. This is a power function, so if you integrate a power function on basically on a bounded interval, that integral is going to be finite no matter what. Okay? And yeah, so I'm going to basically take that and yeah, I'm going to apply it. So since it is finite, okay, again, we already know what it is, but since it is finite for the Wiener process, we can apply Fubini's theorem. And so this allows us basically to address the expectation of that stochastic basically integral that you see, right? So that is basically where you have the stochastic version of the Riemann integral. The expectation of the integral is going to be the integral of the expectation. And since the Wiener process has zero mean, this is going to be, I mean, you can see this right here. Okay, so we are applying it right now. Okay, so we are applying this. Okay, there is the integrand missing, but everything else is there. Okay, now what is the expectation of the Wiener process? Actually, by definition, we talked about it. This is 0. Okay, so the expectation of 0, well, if you integrate that, you have 0 coming out, so this is not going to be a big deal. So the expectation of this integral is going to be 0. All right, does that make sense? Okay, so that is basically one issue. Again, before you apply it, we need to check. It can be applied if, for example, this function or this integral exists, which means it is finite. So if I say it exists, I mean its finiteness. That's what basically what literally it means. So the expectation of the corresponding Riemann integral, where the Wiener process is involved, is going to be 0. Now, what about the variance? But I'm going to basically address that too. So again, I'm going to address the variance later, but that's basically just giving you the application. I basically was not addressing when does basically the Riemann version exists. So there is going to be two conditions. That is going to be condition 1 and condition 2. Okay, so you have a partition again, and so basically where you have Si asterisk somewhere between Si minus 1 and Si. It doesn't really matter where it is. And then basically the integral exists, which means that this sum here is going to be, I mean, when it comes to a limit, the limit of this sum, the mean square limit of this sum, to be precise, right, is going to be finite, right, in terms of basically a random variable. So that is supposed to be the case. Okay, so then this means that the integral exists. Again, this is just a symbolic notation. You can skip it if you don't want to. Write it down, but this is the importance here. The finiteness, which means that it exists. You understand the point? It exists. And let me make those statements right now. Okay, so we're going to see it. If, okay, so as basically the number of subintervals is increased, if and only if, so that is going to be both sufficient and necessary for their existence, the following integral is existing, which means that, you know, you have some sort of limit, which is basically the case. It's going to be a little bit harsh at the beginning, but it will help you. So first off, there is going to be f, which is, you know, the deterministic function by which the stochastic process is multiplied by the expectation, which you see, okay? But not just that. You will need to extend this a little bit. There is going to be a double integral. So you need to integrate twice with respect to s and with respect to r, okay? Which is not a big deal because you can integrate basically first with respect to x, for example, and then with respect to r later on, or first with respect to r and then with respect to s. It doesn't really matter, okay? So it might be a little bit confusing, but I'm going to apply this. So don't worry, you're going to see an example where some sort of double integral is going to be applied, but this means that you need to integrate twice in this case. If this integral is finite, and then you see basically some sort of autocovariance function. By the way, I'm not sure if you're recognizing it, given that the expectation is 0, because the expectation of the product minus the product of the expectations is the autocovariance of the process, right? You see? So this thing, including basically the whole issue, needs to be finite. It needs to be existing, which means that this function needs to be Riemann integrable. Keep that in mind, guys, and that's the reason why I was talking about Riemann integrals at the beginning. This is a this must be a Riemann integrable function, and it is a Riemann integrable function if and only if this function as a whole, right? So fs times fr times the expectation of the products of the stochastic process is continuous almost everywhere with respect to both arguments. So not just basically on the, you can call it the S axis, but also on the R axis. Okay, so you have basically two arguments. And it needs to be continuous almost everywhere. That is basically the necessity and the sufficiency for this function to exist. Okay? Okay, so that needs to be finite. And if it's finite, then the stochastic Riemann integral exists. And if the stochastic Riemann integral exists, then this is going to be finite. So I'm going to basically prove both directions. Okay, so let's see it. I'm going to show you basically how this works. Okay, so you need to prove two things. First, number one, if this is true, right? If this is true, then the previous integral exists, the double integral with the autocovariance, right? Okay, so basically that exists. I'm going to show you that, so you see basically what it will be. Okay, now if it's finite, then what? Okay, as basically n is increased, so as basically the number of subintervals is increased on the partition, right? Then what? Okay, so first, again, you need to understand this. Then basically the variance must converge because you have mean square convergence. I'm not sure if you remember that statement regarding the mean square convergence, what the consequence of that was, but among others, if basically a sequence of random variables converges to a limiting random variable in mean square, right? That was it. Then the expectations do the same thing and the variances do the same thing. I was actually proving that statement. Okay? So that, as a consequence, among others, is that the variance needs to be basically converging. Okay? So again, I'm not sure if you understand that, but let me just basically recall to which I'm referring to. So let's say if a sequence of random variables converges in mean square to a limiting random variable, so does the expectations. Okay, so the expectations do the same thing. Okay, so the expectation basically, I mean, it's not a mean convergence, but this mean square, but this is basically the deterministic one, and the variance too. So since basically the variance converges, well, this means that the second moments are also converging. You see, I mean, that is basically one of the consequences. And that's basically the statement that I'm trying to make right there. So the expectation of the squares, which you got basically here, of the sum, right? So of the sum above, is going to converge to the expectation of the square of the integral, right? Because otherwise it would not be working. And this is going to be addressed by Fubini right now. Okay, so again, if, you know, you can do it, the expectation, I mean, okay, first of all, I would need to get rid of the squares, but that's not going to be difficult. So I'm going to show you how to. But this is going to be actually finite. And I'm going to show you that this expression is going to be equal to the double integral that you just saw on the previous case. And since it's finite, because otherwise it would not be, you know, you would not have mean square convergence. Thus, it implies that, you know, if the stochastic integral exists, then you'll have the double integral that also exists in. Okay, so that is going to be the issue. Now I'm going to show that quick, so this is not going to be a big issue, but I'm going to take that down a little bit. So first off, I keep the expectation operator, okay? And since I got the square, I will need to basically just multiply two integrals by each other. So the first one is going to be here. That's the first one, okay? I take that. And times the second one, which again, I take it, is going to be here, but I'm going to call the integrator differently. But it doesn't really matter, just renaming it that there are two different distinct expressions. Okay. Now, what you can do is, since these expressions are supposed to be real, because why? Because there is convergence, right? Regarding this, so stochastic integral exists. You can also take that as a constant and put that inside the other. So I'm going to write it down first, okay? So I'm going to take basically the other one, okay? I was simply just writing it down, okay, for the moment. And then I'm going to take it out, and I'm going to squeeze that in as a constant, okay? So I'm going to basically push to the side. I'm going to squeeze that in as a constant into the other, you see? This is something that you can do, okay? Because the integral is actually a linear operator. It is both additive and homogeneous. Homogeneity means that if you multiply it by the constant, the integral of a constant, the constant times an integral is going to be the integral of the constant times a function that you're integrating, okay? So it's basically homogeneity, that is due to homogeneity. And then you can change the order of integration, which I will do, okay? It doesn't necessarily need to be consistent, even basically when you take the differential operator with you. Okay, so I'm going to put that over here, I'm going to put that over here, and even the differential operator can be exchanged. Okay, so the order of integration is not relevant, just as the order of differentiation is not relevant. Okay, and then you're going to apply Fubini's theorem. I'm going to basically apply it twice. So assuming that I can, because again, that was making an assumption here. Okay, so you can take that out. Okay, I'm going to take both integrals out from the expectation operator, and I'm going to squeeze that in. So I'm going to write those things down. And since these functions are deterministic, you can take them out even from the expectation as well. Okay, because the expectation of a linear transformation is a linear transformation of the expectation. And now, since this is finite, why? Because you have that the stochastic integral exists. If the stochastic integral exists, this expression needs to be finite. And this is equal to that. This must be finite too. And that's basically proving the one direction where the existence of the stochastic integral implies the finiteness of this expression. And that's basically what the major result is. That is basically the first one. Okay? So again, I'm going to summarize. Okay, so this is basically what we had done. That was a previous statement. If this integral exists, which means that the limit of the sum, of this sum exists, right? As the number of subintervals increased on the partition, then this sum is this expression, which is a deterministic one, since it's an expectation, isn't converging to that, and that expression equals the double integral that you saw, which is also finite, because the moments are also converging if a sequence of random variables converges in mean squares to another. All right? That's basically the issue. Okay? Now, I will need to basically find the other direction. So I'm going to show that if the double integral is finite, then basically the stochastic integral exists. And I'm going to use basically in this case the logical negation. So if A implies B, which is supposedly be the case, then the negation of B is implying the negation of A. So that means that if it doesn't exist, then it's not going to be finite, which basically generates equivalency. So I'm saying the following thing: if this integral does not exist, which means that there is no mean square convergence, right? You see? Then the other does not exist either, okay? Which is basically showing the equivalency, okay? So one does not exist and a stochastic integral exists and the other is finite, which corresponds to the double integral. And if it's not, then basically there is divergence here for this expressions too, which means that if A implies B and the negation of A implies the negation of B, then A is going to be equivalent to B, and that's basically illustrating the technique of the proof, okay? So I'm going to basically talk about that, right? Okay, so let's see. Now, first off, again, I will just leave the expectation operator, okay? So first, again, once one factor comes here and the other factor comes there. And since the summation order is not relevant either, so you can basically change it whenever you like to, which I do, okay? So again, I'm just playing that with a little bit. It's just a simple sum. So basically what I did with the integrals, you can also do that with the sums, by the way. So you can basically change the order. And the expectation of a sum is a sum of the expectations. So I bring the expectation operator into the summands. and I'm taking out the deterministic functions. Okay, so those are the deterministic expressions, right, which are involved. And then the only stochastic expressions are here. Those are the two. And yeah, the expectation of the product, in this case, which again, in this sum, is going to be here. All right, so that's basically how you bypass it. Now, if this is not convergent, right, which it's not, supposedly be the case, then the other thing is not convergent either. Okay, so that's it. Why would it be, right? And that is basically the issue. Okay, so yeah, and that's illustrating basically equivalency. Okay, so that was it, by the way. Okay, just to remind you guys, you will not need to do these things in the exam. So I don't want you to basically to learn these proofs by heart. It will not help you. Okay, if I'm making a statement, I'm basically trying to be as accurate as I can be to proving that. Okay, so whether basically the stochastic integral exists or not can be determined by the double integral that you just saw. And now I'm going to apply this on the Lemma for Wiener processes. Okay, so basically I'm going to check whether basically the later on. Okay, I'm going to make another statement now. Okay, so we'll see. But I want you to remember basically this issue. So I'm going to look at the Wiener processes and check whether basically they're corresponding stochastic integrals, stochastic Riemann integral exists, by the way. So I'm starting basically by the partition, and I'm going to give you basically the other statement for the existence of stochastic Riemann integral. So that's going to be statement number 2. Again, the first statement was an equivalency. The stochastic Riemann integral exists if and only if the double integral that you just saw is finite. And now I'm going to give you a sufficient condition. Okay, so here in this case, you're about to see a sufficient condition. So if you have the sum that is supposed to converge, okay, this is the extended stochastic Riemann integral, by the way. Okay, so it is basically true that this exists, right? Okay, so which means that supposedly be finite, as you see, right? So existence means actually the finiteness of this integral in terms of a random variable, by the way. Okay, so in terms of convergence, right? So there is a mean squared convergence. Okay, that's basically the issue. Okay, now, as basically the number of subintervals is increased in the partition, if, okay, and just basically, if this function here, or sorry, the deterministic function fs, and the expectation of the products, okay, in both arguments are continuous, actually almost everywhere. Now, why is that? Because in this case, the function, and that's simple, and I'm going to base that statement on the previous one, and that is also actually equivalent, by the way, because in this case, the function of the double integral that you just saw is going to be Riemann integrable. Okay, a function, again, keep in mind, guys, a function is Riemann integrable if and only if it is continuous almost everywhere. And that's the point. Okay, because if these two are going to be continuous almost everywhere, then actually the product will be Riemann integrable. And that product was basically part of the integrand of the double integral that you just saw. Okay? So this is basically closing the gap. What I'm going to explain. So don't worry. Okay? Again, so to prove that it's not a big issue, if those things are continuous, at least almost everywhere, okay, then what? Then the function that you're about to see, namely f, which was the deterministic function from the stochastic integral, times itself, basically. So you have basically two different arguments, times the expectation of the product is going to be Riemann integrable, basically because a function, so I'm talking about this function, let's call it, I don't know, maybe we call it gamma or something. Gamma depends on S and it depends on R, so two different things. And so if this function is continuous almost everywhere with respect to S and with respect to R, then it's going to be Riemann integrable in terms of that double integral that you just saw. Okay, so it's going to be basically Riemann integrable in both arguments. I'm going to write it down, which means that the integral, the double integral, where you integrate with respect to S and then with respect to R, is finite. And I was showing you that basically the finiteness of this integral is equivalent to the existence of the corresponding stochastic Riemann integral, by the way. All right? So actually, it is enough for the deterministic function that is in basically part of the Riemann integral, stochastic Riemann integral, as well as the expectation of the products, which can be associated by the autocovariances, to be finite. So if the autocovariance of the stochastic process is finite, and the function by which it basically is multiplied is continuous almost everywhere, right? Finite in terms of basically continuous also, right? Almost everywhere. Then the corresponding stochastic Riemann integral will exist, okay? And it's not difficult to achieve that, by the way. So when it comes to basically stochastic processes, it's not difficult to achieve actually continuity regarding the autocovariance, okay? Especially when it comes to continuous time stochastic processes. But anyway, okay? So yeah, but I'm going to show you. So let's see basically an example to this. And I'm going to focus on Riemann integrals with the Wiener processes involved, okay? So again, let me start by the partition, as you know, okay? I'm going to split basically the interval from between 0 and t. And again, so in such a way that basically the starting endpoint is going to be the lower endpoint of that interval, whereas basically the upper endpoint is going to be, yeah, the final endpoint of the partition. And keep in mind, guys, that basically for which the sum is developed here, these expressions, okay, so you have basically Si asterisk is somewhere between actually Si minus 1 and Si. It can be also equal to that. So I forgot to say this. It can be also equal to the endpoints, but it's basically not in general. Anyways, okay, so I apologize. Anyways, if basically the function, which is defined on the compact interval between 0 and t, is a real valued function, is continuous almost everywhere. Let's assume that this is the case, which again, most functions are that you are familiar with. And I have a Wiener process included, which again has a continuous autocovariance. You saw the autocovariance function of the Wiener process, by the way. Okay, so I will see that later on. Okay, but the stochastic integral that I'm going to develop here is based on the Wiener process. The Wiener process is going to be involved. Okay, and for that it is going to be enough that the function by which it is basically multiplied is going to be continuous at least almost everywhere. Okay, so if this is the case, then it is basically what it will be. Okay, now this includes, okay, so the existence basically, or this ensures basically the existence of that integral, okay, and yeah, so that's it pretty much, okay, so it is what it is. And then of course I would need to address the expectation and so on, so you would be able to apply it. Again, W is a Wiener process, and as you might remember, this is what you see is the autocovariance of the Wiener process. And I'm not sure if you remember this, but we were looking at basically for the random walk as well. Okay, so the random walk and the Wiener process coincide with each other when it comes to that, because that turned out to be the minimum of the time points. Again, if you're not sure why, okay, so why is basically the autocovariance of the Wiener process to be the minimum. I think I did this in lecture 4 when I was first looking at the Wiener processes, or 5, if I recall it correctly. Sometimes I cannot recall it myself, but I've done that. So that was basically addressing previous sessions where I was addressing basically properties of Wiener processes. Anyway, okay, so you might remember that. And again, this is the autocovariance covariance function of the Wiener process, and that is of course continuous, right? Almost everywhere, by the way, right? So when it comes to basically time, it's not continuous, but it's continuous because it's not continuous because it switches at a certain point, right? But it's continuous almost everywhere. And yeah, so that is the case. Now, I'm going to address the moments, and yeah, and so see basically what the point is, okay? But assuming that this function is going to be continuous almost everywhere. Now, what about basically the expectation of it? The expectation of that is going to be the integral of the expectation. And since basically f is deterministic, you can take it out, which I did. So you can take it out from the expectation operator, which I did. Now, what about basically the expectation of the Wiener process? The expectation of the Wiener process is 0, by the way, right? So here comes actually the integral for 0, and that's not a big deal, okay? So that is true. And however, the variance is not. The variance is going to be different now, okay? We're going to address this in detail. Now, how would you basically get the variance? The variance is the expectation of the squares. Why? Because variance is, again, so the variance of any random variable is the expectation of the squares minus the square of the expectations. And since the square of the expectation is 0, because the expectations are 0, as you see, the variance degenerates to the expectation of the squares. Now, squares of what? The expectation of the square of the integral, of course, right? Okay, so I'm basically continue from here. And how would you, or how were you addressing that? We were doing this, and I was doing basically work with the proof, right? I was showing you that this expression was equal to the double integral that you saw for the equivalent condition for the existence of the Riemann-Stieltjes, the Riemann integral where a stochastic process is involved, okay? So again, we were doing that. I'm not going to do it again, but this expression turned out to be that double integral. Okay, so first you integrate with respect to r, and then you integrate with respect to s, and you integrate what? The deterministic function at point s times the deterministic function at point r times actually the autocovariance function of the Wiener process, which was, again, you saw the minimum of those time points, right? So we're going to do that and see basically where, okay, we're going to apply this. Now, this is going to be finite because this function, check this out, is continuous almost everywhere. It's not continuous, but it's continuous almost everywhere. There's jumps in a function, but only basically at the finite points, and even the finite points of time, okay? That's why I don't find most of the books consistent, by the way, in that regard, because they say it's continuous. Well, it's not. This function is not continuous. The minimum of basically of s and r is not continuous with respect to s and r, okay? But it's going to be continuous almost everywhere. And that's basically the emphasis, okay? So that is basically what I'm correcting here most of the time. Anyways, okay, so let's replace that with it, okay? And look at the general case where the deterministic function was equal to 1. Then this is what it turns out to be, okay? And now I'm going to take care of that, okay? How would you basically integrate that function? It might be a little bit confusing, so I'm going to slow down a little bit, but you will see basically it's not that big of a deal. And I would like you to recommend this part as an exercise. So again, one exercise, again, I will basically create those, and then you'll find the solutions here on the slide, is calculating the variance of this integral, okay, which is again here already, okay? Now we start from here because we've done basically everything else. Now, okay, what the idea is the following. So I'm going to keep the integral with respect to r, which is going to be there. I'm not going to touch it. It's going to be there. But I'm going to split the other two, the blue one, okay, where I'm basically, no, it's not two, but I'm going to split into two parts. Okay, so the blue one, I want you to focus on that. You can put basically those parentheses around them because the order of integration is not basically irrelevant. Okay, so first off, I'm going to integrate between 0 and r. Okay, again, I was splitting it. Okay, not t, r. Okay, because I was interrupting it. Okay, and then I'm going to continue integrating from r to t. So I'm going to basically split that integral into two parts. Now the question is, okay, if you address this, what is the minimum between 0 and r if basically s is rolling? You understand the point? So s is basically rolling from 0 to r. What is going to be the minimum of s and r? Now if basically s is rolling and you have basically from 0 to, it varies from 0 to r, it's going to be all s all the time. You understand why? Again, so keep in mind, guys, I want to address the minimum of s and r. And s is rolling from 0 to r. So s is always going to be either smaller than r or equal to it. That's the point. So it's going to be always the minimum, at least in this part. So at least in this part, this is basically what the integral is going to be. And then I'm going to add, since I interrupted it at point r, which was the upper endpoint of this interval, I'm going to integrate again from r to t, okay? And keep in mind, guys, s is the variable that is rolling right now. So s is rolling now between r and t, you see? Okay? So s is rolling between r and t. What is basically smaller, s or r, if actually s is rolling between from r to t? Right? Again, so here it comes. And that the answer is r, of course, right? Because r is going to be smaller. It's basically s where it starts at point r, right? So r is going to be smaller or equal to s. But anyway, okay, so if they're equal, it's still the minimum. And that's it. So I was basically splitting this integral into two parts, and I can basically address its antiderivative, okay? What is going to be the antiderivative of that? Check it out. Now, first off, I'm going to take care of the outer integral. The outer integral is the integration with respect to r. That is going to be done later, not now. Okay, so check this out. I can address the antiderivatives, Stammfunktion is a term, right? The antiderivatives of each of the functions. What is the antiderivative of s with respect to s? So which function basically, when you're differentiating it, would be equal to s? And the answer is 1/2 times s squared, right? Okay, so that is basically the antiderivative of s. Okay, plus c, but skip that because we don't need to have that. It's constant anymore. Okay, we're going to look at that from 0 to r, right? Because 0 is the lower end point and r is the upper end point, at least in this integral. I'm going to take care of that later on. And then plus the other one. Now, what is basically the antiderivative of r with respect to s now? It is r times s. Again, keep in mind, guys, I'm integrating or / differentiating with respect to s, not r, s. So r is a constant. And r times s is going to be its antiderivative. And I'm going to take that from r to t, okay, because r is the lower end point and t was the upper end point of that integral. You understand this? Okay? It's not complicated at all. So again, so this is basically just, you know, a little exercise. And I'm going to continue. Okay? On your slide, it's not complete, but it doesn't really matter. I'm going to complete it now so you can watch basically what I would do. Okay? So the outer integral would be the same. It's not that big of a deal. The outer integral is the integration with respect to r. R is the integrator, sorry. So that's not going to be a big deal. Now, if you put r into s, you'll have basically 1/2 times r squared minus 1/2 times 0 squared, because the lower end point, if you're inserting it, the lower end point would be 0. But that's basically what you're left with. Okay? And then plus, because it says plus over here, the other one. If you put the upper end point is t, and the lower end point is r. So s is going to be substituted by t minus r. That's what I'm doing, okay? Because it's a linear function, so it doesn't really matter. So r times t is going to be the upper endpoint minus r times s, r times r, which is the upper endpoint, so that is going to be r squared, okay? Now, this expression, you have 1/2 times r squared plus r times t minus r squared yields negative 1/2 r squared plus r times t. So negative 1/2 r squared plus r times t is the final result here for that, because I was basically simplifying this a little bit, okay? And then I'm going to continue from here. Now, this function can be integrated with respect to r relatively easily, okay? We need to find basically their primitive functions. So what is going to be the primitive function of negative 1/2 times r squared? The answer is simple. The answer is negative 1/6 basically times, or 1/6 basically, so times r cubed, right? Because if you're differentiating that, you're going to get that back, okay? I think it's basically, for me, it's always easier to differentiate than rather to integrate, but again, it's just me, okay? Next, we're going to look at basically the primitive function of r times t with respect to r, because we are basically integrating with respect to r, and that is a linear function, so it's going to be the parabola 1/2 times r squared times t is its primitive function, and then you integrate basically from 0 to t. Now, if you integrate a polynomial from 0, that's going to be 0, okay? There is no constant involved, so that is going to be 0, so you just need to put in t. You need to basically insert t for r, and then you'll have basically the final expression. Now, that's not a big deal because you got negative 1/6 times t cubed plus 1/2 times t squared times t, which is also t cubed, okay? So negative 1/6 plus 1/2 equals, 1/3, right? You see that. So this is basically what you're left with, and this is 1/3 times t to the power of 3, which is t cubed, okay? And that was it. Now, you might remember, okay, where basically 1/3 is coming from for the variance of this integral. That was basically the integrated Wiener process. Remember that? So this is basically illustrating the variance of the integrated process. And that was basically the first statement I was making. And since it fits better to this lecture, again, I decided to skip it from last time, and then you can see this over here. Okay, so that explains a lot why the variance of the integrated Wiener process is as is, or was. Anyways, okay, now in this case, I will basically introduce you to a simple corollary, because the rest is not just that, but the distribution. Since the Wiener process is normal, the sum of normal distribution is going to be the normal distribution itself. Okay, it's not the central limit theorem in contrast to the process, because the Wiener process, again, so the limit is consisting of normal variables. Okay, so the sum of normal variables is going to be normal. Okay, so the integrated Wiener process, as you see, is going to follow the normal distribution. And not just that, but basically this, where if you multiply by the deterministic function also. So it's going to follow the normal distribution, by the way. Okay? And the expectation is 0 all the time. All the time, we saw that. Applying Fubini's theorem, yielding that. However, the variance was not. The variance was this double integral. You might remember that. This is a little bit, let's say sophisticated expression, but it's not that big of a deal if you check it out real quick. So you integrate from 0 to t with respect to r, and then you integrate from 0 to t with respect to s. And then you have the deterministic function at point s times the deterministic function at point r times the minimum of s and r. That was a little exercise which I did, basically where the deterministic functions were equal to 1. Okay? But that's how I was splitting it. And yeah, so you can do it too. Okay? Yes, again, the order of integration is not, it's not relevant. So you can basically take that I will create some exercises based on that one as well. And here is the regular integrated Wiener process as the first statement that I made about that, or the distribution. Basically, it's normal. It will have zero mean, and the variance is 1/3 times t cubed, okay, as we have just seen in the previous case. So I was confirming his information, right? Okay, this is basically what the distribution of the stochastic integral is considered. Okay, now we're going to do the same thing for the Stieltjes counterpart. Okay, so maybe you can start a little bit, and we're going to do that one as well. Okay, so there is a Stieltjes version, and again, so it always starts by a partition, and so you have seen that definition already, so I'm not going to elaborate on that much longer. Okay, but that's not going to be some extension here. Okay, so the issue is what I want to stress here is that I'm going to put my considerations on basis of Wiener processes, in Wiener processes only. Okay, so that should be basically reminded you. Okay, so the integrator will be the Wiener process. This is a specific type of the stochastic Riemann-Stieltjes integral. Okay, but again, I was giving you the general definition. Anyways, okay, so what was that? That was a deterministic function. It has nothing to do with the deterministic function of the simple or the regular Riemann counterpart. The deterministic function times the increments of the stochastic process, okay, on that partition. So when you look at basically the increments of the stochastic process, the Wiener process, by the way, on that partition, okay, the Wiener process has independent increments, just saying, right? You know that for a fact. And there is just going to be a function, a deterministic function multiplied by it. Now, again, SI asterisk can be somewhere between the upper and the lower endpoint. I was not telling you that, but if this thing is finite in terms of a mean square convergence, okay? So where actually, again, SI asterisk is somewhere between the lower and the upper endpoint. It can be also equal to it. I apologize. Okay, I would need to basically to fit that. If there is on the slide, I will correct this. Okay, so there can be equality there regarding the increments. Usually it's not, but it doesn't really matter. So you can take basically either upper or the lower endpoints. Anyways, then what? Then basically the mean square limit is actually set to be the stochastic Riemann-Stieltjes integral of the function, in this case, with respect to, now, in this case, the Wiener process, and the Wiener process only. Again, I will basically talk about in conjunction with the Wiener process, but keep in mind, basically the point SI asterisk can be anywhere between within the ith subinterval of the partition, okay? Okay, guys, yeah, so if this is true, okay, so if basically this is finite, actually, then it is basically the issue. Now, I was not addressing their existence, and so I would need to basically make that statement, basically. Okay, when does that exist? It exists, for example, again, then it is blah, blah, blah. Okay, so you need to address it. If, for example, the function is continuously differentiable almost everywhere. Continuously differentiable, what does that mean? It means that its derivative is going to be continuous at least almost everywhere. Okay, so it's differentiable and its derivative is going to be continuous almost everywhere. This is basically what it means. Okay, so it must have a derivative, because if it has, at least on the interval, if it has, then it can be basically rewritten, and I'm going to basically adjust this using integration by parts. It can be rewritten, so if you consider integration by parts, the German term is partielle Integration, This is going to be the deterministic function at point t times the Wiener process at point t. And then, of course, you have basically the lower end point, which would be 0. But since the Wiener process is 0 almost surely, I will skip that. So you have minus the integral between 0 and t of the derivative n times the Wiener process. And what you see here, and I want you to remind you on that, what you see here is a regular stochastic Riemann integral. So one of the conditions basically, I mean, this is just a sufficient condition, not a necessary one, but it's at least a sufficient one. So if the function that you're looking at has a derivative, right, which will have at least almost surely, okay, so within that range, then it can be expressed by basically the stochastic Riemann-Stieltjes integral can be expressed by a stochastic Riemann integral. That's a point. Okay? So everything which is true for the stochastic Riemann integral will be also true for its Stieltjes counterpart. You understand the point? And all you would need to do is just basically addressing variances and so forth and whatever. Anyways, okay, so by the way, and again, why is that? Because integration by parts yield just that. Okay, so here is basically the justification for it. But it has to have the derivative to basically to be able to address it. Otherwise, this would be just the expression. Okay, right? Which is actually a Stieltjes version of the Wiener process. Now, how to deal with that, this is just a matter of it, basically a different issue, but if it has a derivative, so if the function has a derivative, it's basically preferable to write it like this. All right? So, yes, and okay, so let's prove this, okay? And then we take a break. I think it would be the case. Nice. All right? Now, the function, which was the derivative, is supposed to be actually continuously differentiable. And the other function is actually, I mean, this is, both are continuous, right? I mean, the derivative is, it can almost everywhere. This means that basically the derivative times the autocovariance of the Wiener process is Riemann integrable, right? Simple as. And that is also going to be true if you multiply it by itself for basically for another argument. So this function here that you're just seeing right there is going to be continuous almost everywhere with respect to both arguments, with respect to s and with respect to r. Okay? Now, especially, I don't basically keep in mind, guys, this is equal to the minimum of s and r. And yeah, so this is basically what I was basically just mentioning here. Okay, so that is just a minimum of s and r, and that's it. Okay, now in this case for the Wiener process, of course, right? Yeah, so this is Riemann integrable in both arguments, but you would need to, the general case, if this is not a Wiener process to which you're referring to, you would need to check first. Okay, and yeah, so what does that mean actually? It means the following: if you integrate this with respect to s and then with respect to r, then the integral is going to be finite. Plain, blank, simple. Okay? Why? Because this function is continuous almost everywhere. And if the function is continuous almost everywhere, it's going to be Riemann integrable. Point blank, simple. We already had that. Okay? It doesn't need to be continuous, guys, to find its basically its area. Okay? But continuous almost everywhere. That is one necessary condition and sufficient condition for Riemann integrability, and that is, it just extended basically to the two-dimensional case. Simple as. Because this function is already basically continuous almost everywhere. Now, again, so in this case, this is basically what it is, right? You saw that, so that is true. Okay. Now, here, I'm going to look at basically the further existence of the of the stochastic Riemann integral. Okay, and then well, actually, or it would be basically better if you took a break right now. Let's take a break because that would be a new subject. So let's take a break now. And later on, we'll basically continue with the example that you are looking at. Just a moment. Here, I will just stop the recording or pause it, and then we're going to continue later on. All right. Okay, so we are going to look at an example for the existence of stochastic Riemann integrals. Now we're going to basically look at a function, deterministic function, with respect, and just integrated with respect to a Wiener process. And then if the function is equal to, let's say, to the identity, which means that you have basically the identity, then the question is what happens. Now, first off, if you replace it, basically, okay, so I'm just basically writing out the stochastic part, and then you'll have the identity, okay, you would need to replace basically the function by the identity. So you integrate the function s with respect to the Wiener process. And the question is, what is it? Now, here is the answer. That was a formula, and I would like you to remember this formula. So you have the deterministic function. I mean, of course, the identity is a continuously differentiable function. So based on that, or based on integrating by parts, you have the deterministic function at point s, at point t, by the way, times the Wiener process at time point t, and then minus the integral from 0 to t of the derivative of the continuously differentiable function times the Wiener process. Okay, so that is basically what you end up with. Now, if you apply this thing for the identity, you have t at point t, right? So t is basically the identity, times the Wiener process, and then minus, you got the integral from 0 to t of the derivative of s with respect to s. Now, the derivative of s with respect to s is 1, of course, right? So you got 1 times the Wiener process. You can skip 1, by the way. And that is actually the regular. So this part is actually just a regular Riemann integral for the Wiener process, which has a distribution, which has a normal distribution with mean 0 and a variance 1/3 times t cubed. You might remember that. Okay? And it's simply just subtracting here from t times the Wiener process. Anyway, okay, so that's actually it. Okay, if the function is equal to, let's say, 1 minus s, as you see, right? So you're at the top, 1 minus s. Then what you do is the following. So you replace the deterministic function, or you basically insert it. You have 1 minus s, which is simple. Okay, now in this case, this integral, according to this formula, requires the function at time point t, which is 1 minus t, right? So as you see, 1 minus t, if you insert t into that function, you get 1 minus t back, times the Wiener process at time point t, which is here. And then, of course, minus the derivative of 1 minus t, I mean, basically for the integral, is going to yield a plus sign, because the derivative of 1 minus s with respect to s is going to be plus. So here comes plus the integral from 0 to t times 1, which is actually, degenerating to the Wiener process that is integrated with respect to s. You see that? Okay, so again, the derivative of this function, okay, I'm going to write it down here with respect to s, is going to be -1. And since basically -1, I mean, if you take the integral of -1 times the Wiener process and you subtract that integral, you can simply just add it. Okay, so that is basically eliminating itself, and this is basically what you'll have. Okay, the last one which I use is just simply 1. Okay, so that is just simply a constant. So you simply just replace the deterministic function by a constant, which is equal to 1, so you would not need to have that actually at all. but you can go on. So that is basically the Wiener process at time point t minus its starting value, which is 0 almost surely. And since this integral is equal to 0, you can simply just skip it. Okay, so you do not need to have it anyway. I mean, this is elementary, right? So if you sum up basically the increments of the Wiener process, you end up with the Wiener process at time point t. Since basically because the starting value of the Wiener process is or was equal to 0. So that's that. Okay, so things like these are going to be relevant for the exam. Let me stress this. And so thus I would like you to remember at least this formula. Okay, so you can, this is basically how to address stochastic Riemann-Stieltjes integrals if the Wiener process is involved, which is going to be the case. Okay, so that is going to be an exam, basically something which I would look up. All right, now next I'm going to look at the moments, expectation, invariance, and so forth. Okay, so now assume that the function is continuously differentiable, at least almost everywhere. Okay, because that ensures that, you know, the stochastic Riemann-Stieltjes integral exists among others. So then, of course, I can basically address this expectation. Now, how would you basically calculate the expectation? We'll confirm this later on. This is just, you know, a little stress here. I mean, the expectation of that is going to be 0. It's not a surprise. Okay, you can simply, I mean, you're not supposed to just simply just bypass it by the integral as Fubini's theorem would suggest, because that is a different thing if you have that as an integrator, but you can apply it on this one. Okay, and here you can bypass it, so that is going to be a point. Now, again, but I'm going to look up to it. Regarding the variance, I did this when I was a student, and it is brutal. Okay, so I'm going to prepare that as a solution, but don't be scared. Okay, that will be a little bit too, let's say, it's not difficult, but it takes time. So you're not supposed to give up regarding the integration. Okay, I did it, and again, it takes a little time, so I decided not to present this. But simply, this is just going to be the integral of the square of the deterministic function that is involved here for the Stieltjes version, okay, of the stochastic integral. Now, it might sound intuitive, again, because, you know, you have some sort of 0 expectations here, and that goes away because the variance is finite, and so on and so on. And you could simply make the argument that the variance of the Wiener process, or the differential of the Wiener process, would be just simply just dt, by the way, which, again, this is not a wrong statement, so then it makes more sense, because then you would square it, but it's not that easy. Okay, so that's basically not wrong, but it's not correct either. You cannot bypass basically the variance separated by the integral. So again, because the variance of a sum is not the sum of the variances, although basically you have the independent increments, by the way. Okay, so I'm not going to elaborate on that, but this is just a different story. If you look into, I mean, again, I will declare it as to be an exercise, so you can check it out there. But it's going to be a little bit too, let's say, too hard in the sense. It's not difficult, but it takes time. It takes a lot, real effort. Okay, but maybe you can check it out, and then you can practice integral calculus if you like. But it's not going to be that harsh in the exam, so it's not going to be that big of a deal. Anyway. Surprisingly, or not surprisingly, actually, the autocovariance of the process is going to be simply equal to its variance. And the reason, of course, is because the increments of the Wiener process are independent. They don't overlap with each other. So if you go by this integral from 0 to t, and then plus from t to t plus h, you find that basically between the time horizon t and t plus h, there is no overlapping Wiener process anymore, so it's going to be equal to its variance. This is also a little, let's say, harsh if you look at, I mean, you do this by this formula, but again, you can check it out. It takes even more time, but I was basically doing it, and you can look into the solutions of the exercises simply if you feel like giving up, but maybe you, if you want to practice integral calculus, that would be definitely enough. I did it. I took the notes when I was a student, and basically, so I will prepare it as an exercise. But again, you would not need to look into that, just if you feel like you will need to practice a little bit. Anyways, now I'm going to look at the distribution of the Riemann-Stieltjes integral. It's not difficult to address it because it will be normal, all right? You have the Wiener process involved, and the increments are normal, so thus the limit will be also normal. It's not a surprise. Actually, in that sense, the expectation is going to be 0 because that was the mean here of the stochastic Riemann-Stieltjes integral, so that was the mean of that. And then you have the variance, which was the integral of the square of the deterministic function. So the square of the deterministic function, I mean, again, so you have that basically here. This is it, all right? So that is basically what the variance is going to be. And based on that, I'm going to solve another exercise here where you would need to address just that for the 3 functions that I was actually addressing for, I mean, when I paused the Riemann, or the distribution of the Riemann, regular Riemann integral, or the stochastic regular Riemann integral then. Okay, so that is also not a surprise, again, because the normal distribution is reproductive with respect to sums, and also with respect to linear transformations as well. So it's not a surprise. Now, I'm going to look at these examples. So the first example for the deterministic function was the identity. And in this case, I'm going to address the distribution of the corresponding stochastic Riemann-Stieltjes integral with the identity. So you have simply just basically the identity function. All right. Now, I mean, first off, you would need to address it. So the square of that is simply just going to be, and again, you have it here, is simply just going to be s squared. So you take s, okay, take its square multiplied by itself. This is going to be s squared. Then you need to find this integral. Okay, so things like this are going to be also relevant for the exam. It's relatively easy. I'm not going to give you difficult functions. If the antiderivative of a function is not clear, I'm going to give it to you after all. All right. So, but that just basically makes sure that you're going to prepare it. Okay. So again, I will create an exercise for that as well. All right. Now, okay, what is going to be? So first off, again, the mean will not change. And what about basically the antiderivative of s squared? Now, the antiderivative of s squared is 1/3 times s cubed, right? So that is not a surprise. Now, here I got t cubed already because the upper endpoint is t and the lower endpoint is 0. And if you put basically the antiderivative at the upper endpoint, you're going to get 1/3 times t cubed. And at the lower endpoint is 0 because 1/3 times 0 cubed is going to be 0. So you have basically the upper endpoint minus the lower endpoint yielding 1/3 times t cubed. And that is going to be the variance, by the way. So you can see this right there. Okay? Okay, so that is actually how it works. And that was it, this part. Okay, so things like this are going to be also relevant. Please make sure that you prepare them. Okay, I will create an exercise, but since I have to record the lecture, or re-record basically at least the first half, probably you're going to see the exercises tomorrow. But anyway, you're going to see them anyway. Okay, so the next example is going to deal with 1 minus s. Okay, so that was it. Now, 1 minus s is a deterministic function now. Its square is going to be 1 minus s squared. It's not a surprise, right? And now, how would you basically integrate this function? You need to find basically its antiderivative. The antiderivative, of course, since the chain rule is involved, because keep in mind, guys, the inner derivative is -1. So this is going to be minus 1/3 times 1 minus s times, to the power of 3. This is basically the antiderivative, as you see, right? Because if you differentiate that with the chain rule, you're going to get it back. So keep in mind the inner derivative, guys, with respect to s is -1. And if you put that basically at time point t, where basically the upper end point is going to be here, that is it. Okay, so that is basically it. And the lower end point now is not going to be 0 this time. It's going to be, I mean, a lower end point, if you put in 0, you're going to have negative 1/3 times, sorry, here is 0, not t, here is 0, right? So negative 1/3 is going to be the lower endpoint. If you subtract that, you're going to get plus 1/3. So that is it, okay? So again, let me repeat. So here it comes. So the antiderivative at point t is negative 1/3 times basically the brackets to the power of 3 of 1 minus t. Okay, so that is the upper endpoint. So where you put basically the upper endpoint into the antiderivative, and then you subtract the lower endpoint, which is negative 1/3, and negative 1/3, if it's subtracted, is basically added to it. So this is basically what the variance would yield. You understand the point? The variance itself is not negative, keep in mind, although because 1 minus t is actually negative if to the power of 3 if basically t is less than 1, okay? But that would be basically the case without loss of generality, by the way. So that is it, okay? Now, if basically you're looking at 1, which is the other case, we'll simply just replace it by a constant. 1 squared is 1. It's not a big deal, okay? You can actually just skip it, okay? And what is basic, but not regarding basically the integral, because what is the antiderivative of that? The antiderivative of that with respect to s is, of course, s. And if you basically insert t and then 0 and subtract the 2, you end up with t. So that is basically what the variance of that is going to be. So if you have actually just the increments of the Wiener process, this is just going to be the variance. I mean, if you have that, we saw already that that was equal to the Wiener process at time point t. And the variance of that is going to be just t, okay? So that's not a surprise actually at all, but I was applying it with this formula. Anyway, so that takes time, guys. All right, but that's something which is supposed to be clear. Now, we're going to look at finally, and that's going to be the final part, we're going to look at the Ito integrals now, okay? But I will focus on Wiener processes only. So this time I'm just basically focusing on Wiener processes, where Wiener processes are involved. Okay, at least basically for the integrator. Regarding the integrand, that's going to be a different thing, but at least for that one, this is basically what the issue will be. Okay, so here it is. This is actually the partition. Okay, so you have the partition right there on this, basically on this interval. Okay, from 0, I mean 0 would be basically the starting point. You can see that right there, okay, and t is basically the upper end point, and you saw actually what the Ito integral is, but only I'm basically focusing on the context of Wiener processes. And the major or the most important part regarding the Ito integral was that it only considers basically the Wiener process, which is the integrand right now, the Wiener process at the lower endpoint. That was it. Okay, so maybe you can just, this is not something where you can simply just go anywhere you like, okay, between the upper and the lower endpoint of the ith subinterval of the partition. It's always going to be the lower endpoint, nothing else. Okay, so you're not supposed to go anywhere else. Anyways, okay, so then this is multiplied by, and you can see this over here, the increments of the Wiener process on that partition. Okay, but again, I want to stress this. It's always going to be at the lower endpoint, right? Regarding the Ito version. The Stratonovich version is the middle, right? So where you have a trapezoid, but not this case, where you basically have the lower endpoint only, and only the lower endpoint, by the way. Now, you have mean square convergence. Again, for the Wiener process, it's not a big deal. We already see or saw what this integral was. But if there is basically convergence in mean square, and since it's basically just the lower endpoint, I will put a negative sign here to it, meaning that it refers to Ito calculus, by the way. Okay? And I'm going to be very consequential with this, even when you look at Ito's lemma. Okay, so this is just just something which I wanted to remind you of. Okay, you can see this over here. So as basically this increase. Now, here you see what the mean square limit is. Okay, and we already had that. So in this case, if basically this exists, then it is the Ito integral of the Wiener process. But the Ito integral of the Wiener process already exists. We have seen that. So this thing is going to be, I mean, in that sense, it's finite in the sense of the mean square limit. Okay, we saw that. In a general case, it's not necessarily existing, but for the Wiener process, it does. Okay, so there is no if here, because actually when the Wiener process is involved, both for the integrand as well as the integrator, then this integral exists. We have seen it already. So we have seen it. So we don't need to establish sufficient or necessary conditions for its existence. Okay? So it's already there. Okay, and the mean square limit is actually there. So we saw this in a previous lecture. Okay, I'm not going to repeat this again, how to derive it. It was, not very sophisticated. I mean, it was not ambiguous, basically. But again, 1/2 times the square of the Wiener process at time point t, which would be actually if the Wiener process was differentiable, that would be the derivative of that. But you have minus t. And where does that come from? And you might remember that. Basically, this coming from the fact that the quadratic variation of the Wiener process is or was finite. Okay, you might remember that one. Okay, so, and that is the case. And the absolute variation is not. So the absolute variation is not, but the quadratic variation was finite. If it's finite and it's not zero, then the absolute variation is divergent, but that was the case for the Wiener process, which I was looking into. Okay, so now, again, so let's see basically what the expectation and so forth are, because these are the moments of the Ito integral where the Wiener process is involved. This is not difficult to address because we already know what the integral was or is. So as soon as you got it, basically you can address it in terms of the expectation and the variance and so on, because we already see. But again, I wanted to summarize it. Okay, so you're going to see it. What is the expectation of it? Now, again, the expectation of the Ito integral is 0. Okay, and that's not difficult to basically to see, right? I mean, the expectation of the square of the Wiener process was the variance, so the variance minus t, which would be basically the variance is also t, so that is going to be 0. Again, it's not surprising, but you're not just supposed to just simply bypass, regarding basically, looking at Fubini's theorem and so on, because you need to understand that the integrator is also stochastic. Okay, so this is not just basically working like this, as that was the case for the Riemann integrals. The integrator is also stochastic, so you not just simply can bypass the expectation operator by the integral. And the same is true for the variance, by the way. So I'm going to take that, and I will basically address its variance. Now, the variance of that, based on the normal distribution, and we're going to show this one, is, again, that takes more time, by the way, but based on the fourth moment of the normal distribution, which is known to be 3, at least for the standard normal distribution. So based on that, because we already seen that one, it is going to be 1/2 times t squared. Okay, so that is going to be actually the variance of the Ito integral. Okay, now, that is also a good exercise. So I basically highly recommend this, but after this lecture, again, I'm going to put those things and create an exercise out of it, so you can basically just review these things by solving it yourself, and that is going to be even more helpful. Okay, now, it's not difficult to show, so I'm going to basically address this, okay, here from now on. Okay, so first off, basically the expectation. Okay, now the Ito integral was known to be, and that was basically the topic of actually lecture 5, if I recall it correctly. So 1/2 times the square of the Wiener process minus t. And this can be addressed relatively easily because the expectation of the linear transformation is a linear transformation of the expectation. So you can simply take out 1/2 from the expectation operator. Okay, and then you can simply just, look at the expectation of the square minus t, right? Because this is basically what you're left with. And so then you can also take out t from the expectation operator, which I will. So then you have 1/2 times, but in parentheses, of course, because you need to have it in total, the expectation of the square of the Wiener process, which is going to be its variance, by the way, minus t. So you can take out t from the expectation operator, which I did. Okay, it's a constant in terms of basically it's not random, so that's basically what it is. But you have to have those parentheses here, otherwise it would be not consistent. Anyway, so 1/2 times, now what is basically the expectation of the square of the Wiener process? This is its variance. You just saw that, right? So the variance of the Wiener process, minus t, by the way, inside the parentheses. And the variance of the Wiener process is t. So you have 1/2 times t minus t, which is 0, right? So, and that's the reason why basically the expectation of the E2 integral is 0. Okay, so that's basically the first part. Okay, that's that. Okay, that's not difficult basically to see and to calculate, but I would basically also recommend you to do it. Now, regarding the variance, this is going to be a little bit more difficult. Okay, again, because you need to have the fourth moment. The variance of that. Now, first off, I want to remind you that if there is a multiplicative constant attached to a random variable inside the variance operator, you can take that out, but you will need to square it. So that's going to be 1/4 times the variance of the rest. Okay, so I would take it out, so this is going to be 1/4 times the variance of the rest. You understand this? Now, the variance does not depend on additive constants. Neither, basically, it's basically if you subtract it either. So this is going to be variance of the square of the Wiener process. Now that is a huge issue because the variance of the square can be addressed by the fourth moment of the normal distribution, which I have done also in previous lectures when I was addressing quadratic variations of the Wiener process. You might remember, but you might recall that. So I want to basically recall that the variance of a random variable, any random variable, even if it's a square, is going to be the expectation of its square minus the square of its expectation. The square of z squared, however, is going to be z to the fourth. So that is going to be the fourth moment of z, in this case, if I'm referring to z, minus the square of the expectation of z squared, okay, which is here. And the expectation of the square has something to do with the variance, by the way, because the variance is the expectation of the squares minus the square of the expectation. So I'm going to substitute by that. So I'm taking the fourth moment, and then you have minus, and then you have basically, in this case, you know, the square, because it is squared here outside, so you have basically just that. And the expectation of z squared is the variance of z plus the square of the expectation of z. All right, so that is a formula which I have also used when addressing quadratic variations of Wiener processes, which I did. Okay, so I will basically highly recommend you to do. Okay, and in addition, so 1/4 times the variance of that. You're going to see this basically later on. So that again, so the variance of some square is, I'm going to continue from here. So that is the expectation of the fourth moment of the Wiener process, right, at time point t, but I'm going to address this later on. And minus the square, again, so I'm going to start just by that, the square of the expectation, and the expectation of what? The expectation of the squares, right? So I'm going to have the square of the expectation of the square of the Wiener process in consistency with this formula, okay? And that's basically what I applied. I mean, I could have done this right there, okay, but I wanted to have that step included, so just basically to break it down a little bit. Now, regarding the fourth moment, because that comes next, okay, if, let's say, a random variable follows the normal distribution, which is satisfied by the Wiener process, although the expectation is 0, but it doesn't matter. With mean mean mu and variance sigma squared, then the fourth moment, the standardized fourth moment of the Wiener process. You can look it up. The standardization goes like this. You take the random variable, subtract the mean, and divide the whole thing by its standard deviation, which is a standardization. And to the power of 4 is going to be actually its fourth moment. So the expectation of the fourth the fourth moment of that, basically, is going to be equal to 3. So the fourth moment of the standard normal distribution, that's just simply it, is equal to 3. Now, why I was not addressing it basically by the standard normal distribution, because the variance, although the expectation of the Wiener process is 0, the variance is not. The variance is t, by the way. And so if I basically go further, the expectation, okay, of that, if the, you have, let's say the centralized fourth moment is going to be equal to 3 times the square of the variance, which is, again, here. That was the square of the variance, you see? Okay, so you're gonna see this after all right? And then that's basically what you end up with. So you see basically that expression. Okay, so we need to have the square of the variance, which is t squared, by the way, right? Because the variance is equal to t. So you have 1/4 times 3 times t squared. That's basically in consistency with the fourth moment based on that. You see? Okay, because the variance is equal to t, so the square of that is going to be t squared. Here it comes. Okay, and here you have the square of the variance, and again, so that would be actually the fourth centralized moment. Okay, so that is basically what the normal distribution would yield. And then you have the rest, which is here, this expression. Minus, so here it comes, minus, and then you have the square of the variance of the Wiener process, which is t. And inside that square you have plus the expectation, or the square of the basically 0. I mean, the expectation is 0, so its square is going to be 0. So it's not going to change that much. Okay, so this brackets, I mean, you have 3 t squared minus t squared is going to be 2 times t squared. That's inside the brackets, and multiplied by 1/4 equals 1/2 of that. Okay, so that's basically what it is. And that was a statement that I was making regarding it. So here, if you clean this up, it's going to be 1/2 times t squared. And that is actually, or was, the variance of the E2 integral. You see that, guys? Okay, so you just basically look at that. But you need to have the fourth moment. In case you need this for the exam, I will give you a hint. Okay, so if there is a task like this where the fourth moment of the normal distribution is involved, I'm going to give you that as a hint. Okay, so you're not going to be left alone. You don't need to know that the fourth moment of the standard normal distribution is equal to 3, but it helps in this case because there is a Wiener processes, so on, and yeah, okay, all right, yeah, and okay, so then what's next? Okay, so I mean, these things are equal. Okay, so we're going to look at the distribution, finally, of the E2 integral. Now, regarding the distribution of the E2 integral, you don't have normality anymore because the square of a normal variable is not going to be normal again. Here I'm going to basically look at the integral, I mean, as you see, okay, the upper end point is equal to 1 without loss of generality. I forgot to stress this. There is no loss in generality if you basically restrict your view on that, okay? But you'll see basically what it will be, okay? Now, the question is, again, what is this? Because, again, this thing follows the normal, the Wiener process at point 1 follows the normal distribution with mean 0 and variance 1. That is a variance, right? That is true. But its square is not. The square of a normal random variable follows some sort of a modified version of the chi-square distribution in general. I'm going to address this later on. So here you see basically what this is going to be about. So I'm not sure if you're not sure what this means. I'm going to define it. So how is basically the chi-square distribution with n degrees of freedom? That is a parameter that the distribution has. And it goes like this. If you have, and it's not on the slide, but you should basically denote this. If you have independent standard normal random variables, okay, so each with mean 0 and variance 1, and each following the normal distribution, and they need to be independent. So they're also IID, right? I mean, they have the independent, I mean, the same distribution, which is normal, but they're not just that, but they're also independent. Then they're the sum of their squares, right? So z1 squared plus z2 squared and so on, plus the final one, okay? So the square of the final one would follow the chi-square distribution. Chi is a Greek letter, okay? So chi-squared, again, to be honest, I'm not sure why the name or where the name comes from. I mean, nobody told me that, but anyway, okay, maybe I could ask ChatGPT that. It is going to be basically following the chi-square distribution with n degrees of freedom. So the degrees of freedom, df stands for degrees of freedom, corresponds to the number of summands that the sum of the squares would have, okay? So independently, I mean, of course, regarding the independence. Now, if this follows basically the normal, I mean, the Wiener process at time point 1 follows the normal distribution, the standard normal distribution, by the way, in addition, right? Its square is going to follow the chi-square distribution with 1 degrees of freedom, because you only have one square, standard normal random variable. So since basically the Wiener process at time point 1 is following the standard normal distribution, right? Its square is going to follow the chi-square distribution. However, so there is going to be some chi-square distribution involved, but you have some sort of linear transformation of the chi-square distribution here. Okay? Now, the chi-square distribution is not reproductive with respect to linear transformations. With respect to sums, yes. If the sum, basically summands are independent, yes. Okay? But it's not reproductive with respect to linear transformations. So there is going to be some transformation involved where you have the chi-square distribution with 1 degrees of freedom. If you have 2, okay, so the time point 2, where the variance would be that, you would need to standardize it. Okay, so there is going to be more standardization involved. So this is some sort of rescaled version of the chi-square distribution, if you like, which I'm not going to address. But there is going to be the chi-square distribution involved. Keep in mind, guys, the Ito integral does not follow the chi-square distribution because again, the chi-square distribution is not reproductive with respect to linear transformations. Okay? But there is going to be some linear transformation of the chi-square distribution involved. Okay? I don't know what, maybe it has a name or so, but it will not be the case. Okay? Anyways, I mean, if you take that out, okay, so you have 1/2 times the square of the Wiener process at time point 1 minus 1/2. Okay, so there is going to be some modified version of the chi-square distribution, which is never going to be less than negative 1/2. How come? Because the chi-square distribution cannot be negative, right? The square of a random variable cannot be negative, and it cannot be true basically for the normal distribution as well. So it's no matter what happens, the Ito integral will never be less, and this is something which you can see this here from this result, than negative 1/2. You see this, guys? Okay, so no matter what, it's not going to be less. Again, if the upper endpoint is equal to 1. That's something which I want to stress here, okay? Unless it is not, but in this case it is. Okay, so between 0 and 1, it's not going to be less than that. All right. Anyways, okay, so this is something which I need to address now. I want to basically talk about Ito integral of Wiener processes again, and then I'm going to basically address the generalization. Okay, so I'm going to look at some generalized version that is involved. Okay, so you'll see basically the Ito integral of Wiener processes. Okay, so here it is. And you already saw that, so I was basically just accelerating this a little bit. Okay, so if blah, blah, blah. I mean, in case of the Wiener process, there is no if, right? Because this integral exists already. So we have seen this before quite a lot of times. But again, just basically being consistent with the definition, that this would have been basically the E2 integral of the Wiener process. You could simply just call it like that. Okay, I was referring to it. Both the integrator as well as the integrand is basically a Wiener process. Now, if at least the integrand is not, okay, then it's going to be the generalized version. So in this case, the integrand will not be. Okay, so there is going to be some stochastic process involved, x, which will be the integrand. Okay, so that is going to be a stochastic process, simple as. And the Wiener process is going to be an integrator. Okay, so you have another, maybe, it can be a Wiener process, again, but this is a generalization. Okay, so you have it over here, and here basically for the limit as well. Okay, so it is the E2 integral of x with respect to the Wiener process now. Okay, and that is to which I refer to as the, and the book also refers to that, so to be basically the generalized version of the E2 integral. Okay, now again, but it's even the more generalized version which I introduced it to does not even require for that to be the Wiener process, by the way. But I want to address that also, at least a little. Okay, so what happens basically when you have that? Now, first off, I'm going to look at the existence. Okay, so when is this basically possible? Because in then the question if arises again. Okay, so here it is basically the question if this is true, and the question is when. All right, so when does that exist? Now, okay, I'm going to basically just name one condition for it. I'm not going to prove it, but I'm going to make it clear why. Okay, so it is going to be existent. Okay, so this statement is going to be true. Okay, if and as basically, you know, the number of subintervals is increased on the partition in a mean square sense, of course, if the expectation of the square of the integrand, so here in this case, for the Wiener process, that is true. The expectation of the square is finite, okay, as you see, so that must exist. It has basically a finite variance after all, okay, because if the expectation of the square is finite, and so is the mean, okay, otherwise it would not be, and it at least, okay, so, and it is continuous, almost surely on this interval, okay, or almost everywhere, because again, it's not stochastic anymore, but again, that's going to be just basically the equivalent, okay. That makes it, this function, integrable, by the way. So that function is integrable, Riemann integrable, by the way, in this case. Okay, I'm going to address this after all, and not just that, but it's not that it has to be Riemann integrable. It has to be basically independent on the increments of the Wiener process. Okay, so that is basically the other issue. You have to have independency at the from the independence. In the textbook, it's even more generalized regarding the time points of the independence. But since basically I just need the lower endpoints, I don't need to basically to put that in the general context. So that's just basically going to be fine regarding basically the existence. Okay. Now I'm not going to prove this, but I'm going to demonstrate that this is going to be the case regarding the mean square convergence. Again, so if these things are both true, then the integral exists. That's the point. Okay. So whether this exists or not, you need to check basically whether this is true or not. This is in short by assumption, and that depends on, so the finiteness of the square, or the second moment basically, depends on the structure of the stochastic process X, which is the integrand, by the way. Okay, so that is the issue. Okay, whether this is true or not, you would need to address it. Okay, so in an exam, if basically that is supposed to be addressed, you need to calculate the expectation of the square of that stochastic process. And then you could answer the question, okay, the corresponding E2 integral based on that, where at least the integrator is the Wiener process exists. it must be basically would be finite in that regard. So that is going to be the case if this is finite, you see, and that is the issue. Okay, so you would need to do that if this comes. Okay, but that's the only thing that I would do. Okay, so check whether it exists or not, and you would need to confirm this. Now, I'm going to illustrate that statement. I'm not going to prove that statement, but you're going to see why this is so important. Okay, if there is convergence in mean square, as I basically mentioned before, then the expectations converge and so do the variances. That was a consequence of that. In order to get the variance, you need to have the finiteness of the square of the integrand. And in addition, if that process is independent on the increments of the Wiener process, that is even going to be more possible to address the integrability. But you are going to see this. Now, if this is true, okay, then what? Okay, I'm going to basically take time and address the moments of this. Okay, so first off, I would need to basically get the expectation first. I'm going to make a statement about it. So if it exists, then what's going to be its expectation? And then what's going to be its variance, if it exists. If it exists, its expectation is going to be 0. Okay, that's not going to be an issue anymore. All right, so that's simple. It's 0. We're going to see why. Okay, so you'll see why this is. And you're also going to see why the variance of that is going to look as you're about to see it. Okay, the variance is going to be the integral from 0 to t of the expectation of the squares. And here it comes again. Because if it exists, right, then this is going to be its variance. But the variance is supposed to be finite, because otherwise there would be no convergence in mean square, right? Okay, so that's a point. Now, when is this finite? It is finite if this function is Riemann integrable. And it is Riemann integrable if and only if it is continuous almost everywhere. We were talking about that already. Okay, so that ensures basically that. It's not just that, but it's supposed to be finite too. Okay, but that's it. Okay, so finite and continuous almost everywhere for that integral to be exist. And that basically creates the possibility for the variance of the E2 integral to be finite of the generalized version. Now for the Wiener process, okay, so if basically the integrand is equal to a Wiener process itself, right? You might remember that. You would need to have the expectation of the square of the Wiener process, which is basically the variance of the Wiener process, and that is equal to 2, and that is finite. So that's fine. That works, right? And so since that would be equal to t after all, okay? So in this case, that would be equal to t. For this example, if this is the case, you will have basically the integral of t, all right? And if you integrate that, this is going to yield 1/2 times, s, sorry, that is equal to s, of course, because the Wiener process at time point s, or the variance of that at time point s, is going to be s. So then it's going to be the antiderivative is going to be, with respect to s, is going to be 1/2 times s squared from 0 to t. So if you put it basically, if you insert t here into it, okay, so if you basically insert t, you end up with, and that's basically the point 1/2 times t squared, which we basically just confirmed in the previous part. So that is consistent with the previous part, by the way. I just wanted to stress this. Okay, you understand this, guys? So we were just basically deriving that. That was 1/2 times t squared was the variance of the E2 integral, where but under this condition, where the integrand is also a Wiener process, by the way. But that is a more general case. Okay, do you understand now why basically this function with respect to s needs to be finite and it needs to be continuous almost everywhere? Okay, and that is a point. So I'm going to basically make that statement. All right, now we're going to show that. So let's see, and that illustrates the validity regarding the existence of that. Because if this is true, then the variance of that is going to be finite, which actually creates a possibility for the convergence in mean square. This is why it actually is so popular, right, regarding convergence in mean square, because it needs to have basically just the variance to be finite. Now, first off, I'm going to start by looking at the expectation of the corresponding sum from which basically the E2 integral was created from. The expectation of a sum is the sum of the expectations. So what you do now is again, just simply put the expectation operator here, and then put basically the expectation of the sum ends, looking at it. So here it comes. Okay, so again, expectation of a sum is the sum of the expectations. And here comes the independency now. If random variables are independent, they're also uncorrelated, which means that the expectation of their products is going to be equal to the product of the expectations. Why? And that is a statement that I'm going to make. Because its covariance is 0. Okay? So you might recall that the covariance of two random variables is the expectation of their products minus the product of their expectations. Again, I think you remember that one. You see? Now, if x and y are independent, then their covariance is 0. And since their covariance is 0, then this means that the expectation of the product would be equal to the product of their expectations, in this case, if the covariance is 0. And it is 0 because, and that's the issue, because x is independent of the increments of the Wiener process. Here it comes, you see? So you can split basically the expectation, and that's what I'm going to do now. So I'm keeping the sum, okay, so the sum starts at point 1 and basically the endpoint is n. And then I'm going to split the expectation of the product into two parts. This is going to be the product of expectations. The expectation of x times the expectation of the increments of the Wiener process. But again, so you have the expectation of x that goes down here, okay, so that's basically what you have. And then you have basically the expectation of the increments of the Wiener process, which will be 0 after all, but you're going to see this later on. Now, whatever the expectation of that is, it needs to be finite. Why is that? Why is that? Because otherwise there would be no convergence regarding the mean square, right? It will be impossible, okay? Why? Because that expression would not converge, okay? And this expression is not converging, the expectation would not converge, okay? So it's not possible, okay? Now, regarding that one, this is going to be 0, the expectation of the increments. I mean, the expectation of the Wiener process is 0 already, so their expectation of the increments is actually 0. So this thing is going to be 0 because you sum up those zeros. If you multiply something which is finite by 0, you end up with basically multiplying it by 0. So, I mean, that is, so you end up having 0 coming out. So the sum of those zeros is going to be 0 after all. So that illustrates basically why the expectation is going to be actually 0 too. Because the E2 integral or the expectation of the E2 integral is going to be the limit of this expression. And that is, again, so this converges actually to the expectation of the E2 integral, but the E2, I mean, since this is going to be 0, the expectation of the E2 integral is going to be 0 after all. Okay, so that's not a big deal. Now, regarding the variance, and that is going to be my final statement for today, regarding the variance of the sum from which basically the E2 integral comes from. Now, the variance of a sum is not the sum of the variances. However, since the expectation of the E2 integral, again, which corresponds to this expression, is 0, as well as that expression is also 0, check this out, the variance is going to be equal to the expectation of its square. So I'm going to take basically the expectation of the squares, okay, which is the, again, and the expectation of the square is going to be, I mean, since this is the expectation of a sum is the sum of the expectations, you have it basically there. So this is how it breaks down to, because that is basically what it would be, okay, regularly. In this case, the variance of the sum is also the sum of the variances because these things are independent, by the way. I was skipping that part, but this is not going to be an issue anymore. Here you have the expectation of the square. And yeah, so I'm keeping the sum, and I'm going to use the independency again. X is not depending on the increments of the Wiener process at time point s minus 1, of course. Okay, so that's the only independency that I need. And that is, of course, basically across the board true for all the partition anyway. So the expectation of the product is going to be the product of the expectations, even for the squares, by the way. That is not going to make any difference. So here I'm going to take it basically the expectation of the square of x, simply just ignoring basically the increments of the Wiener process because they don't depend on each other. You can split it still. And then you have basically the expectation of the square of the increments, which is actually the variance of the increments of the Wiener process. And you already know what the variance of the increments of the Wiener process are, or is, but again, I will address this later on. This needs to be finite. Why? Because otherwise you would not get convergence for the variance. Keep in mind, guys, in case of mean square convergence of random variables, both the expectation as well as the variance need to converge. Okay, regarding basically against basically their limits, right? So you have, or to their limits, basically, or the expectation of the variance of the limit. So this thing needs to be finite, otherwise there would be no convergence of this expression. It needs to be the case. Sequence of random variables, if they converge in mean square, so do their expectations and their variances. And that is also true, that must be true for the E2 integral. So this thing needs to be finite. If it is, it will work. Okay, regarding that, now this is the variance of the increments of the Wiener process, because the expectation of its square is equal to its variance. And the variance is Si minus Si minus 1, which is actually positive, right? Now, this is interesting, guys, because this is going to be, after all, as you see, okay? So when you finalize that, I didn't, but this expression is going to be the Riemann sum of this function here. You see? Si minus Si minus 1. These are the increments of time. So this is the Riemann integral of the expectation of the squares, basically of x, but again, a specific Riemann integral for the for the lower endpoint of the partitions. But it doesn't matter. For the Riemann integral, it doesn't matter whether you have the lower end or the upper endpoint of the partitions, right? And how does that look like? Well, it looks like this. This is what it's going to be. Okay? So that's going to be the issue here for this expression. Now, whatever comes out here out of this is going to be determined by the process x. Okay, so x is going to basically tell you what happens to that if basically this is addressed. Okay, so, but I was not taking any specific example related to it, but if x is equal to the Wiener process, then that is going to be here you're going to see the variance of that, which is equal to t, right? You see? Sorry, s, not t. I was making a mistake because you have at point s, so that is basically if x is equal to the Wiener process itself, the expectation of the square of the Wiener process is going to be its variance, and the variance of the Wiener process is always going to be the time point at which is basically it is looked at. All right, so then that integral would be 1/2 times t squared after all, which confirms actually the variance of the E2 integral. Yes, okay guys, yeah, that was it actually. And yeah, okay, I would have just a little more time, but that was a lot. So I don't want to go further. What I suggest is basically, again, I'm going to re-record the first half of the lecture, cutting it together so you see that video. I'm going to fix the errors on the slides, which again happened to be the case regarding lowering and upper endpoints of integrals, but it's not that, it wasn't that bad, so it will be fine. And after that, I'm going to announce the exercises, and I would like you to ask you to solve them. Okay, so I'm going to put basically all these properties related to Wiener processes and whatnot and their stochastic integrals into one example, which again I kindly ask, exercise which I kindly ask you to solve. And those exercises will be, or the solutions basically will be from the slides, so you can check out the slides, but I will edit the solutions too, so you don't need to check them. All right. Okay, so regarding the expectation and the variance, or especially the variance of Riemann-Stieltjes integrals, you can check that out. So if you want to practice a little integral calculus, you can. But it's going to go beyond, let's say, the exam in terms of not the difficulty. It's really elementary, but it's a lot of steps. But in terms of, let's say, effort, okay, that will need to spend. Okay, guys, yeah, no questions, as I assume, so far. Okay, well, then we see each other next week, and that was it for today. Take care. That was it. Bye. Okay. Thanks.